This is section 10.4 part 2. Frequently we encounter problems that involve pressure, volume, and temperature, but moles remain constant. These use what's called the combined gas law equation, and organizing your data is the key to understanding what type of problem you're dealing with. And so I give you a two-step process. Number one, when you encounter a gas law problem, first organize. Organize the initial and the final conditions of the pressure, volume, and temperature. If you only have initial conditions and it asks a question about moles or gives you a number of moles, then you have a PV equals nRT equation. If they give you a set of initial and final conditions for pressure, volume, and or temperature, then you're into what's called a combined gas law problem. So here's the combined gas law. P1 times V1 over T1 equals P2 times V2 over T2. And these combine the gas laws of Boyle's, Charles, and Gay-Lussac's law and assume that moles are constant. In other words, you're not adding any gas to the system nor taking any away. Let's do a sample exercise with this. Sample exercise 10.6 in your textbook. This one right here says using the combined gas law. And so in this one it says, an inflated balloon has a volume of 6 liters at sea level, 1 atmosphere, and is allowed to ascend until the pressure is 0.45 atmospheres. During the ascent, the temperature of the gas falls from 22 Celsius to negative 21 Celsius. Calculate the volume of the balloon at its final altitude. So the first thing that we want to do is organize our data. And so I set up an initial, final table of pressure, volume, and temperature, so then we can see what's happening. And let's just go through the question and let's take the pieces off and we'll fill them into the table. It says an inflated balloon has a volume of 6 liters. So our volume is 6 liters. Put your units in there too in case they change when they go to a final conditions. 1 atmosphere of pressure, so 1 ATM is what we start at. And it's allowed to ascend until the pressure is 0.45 atmospheres. So our final conditions is 0.45 and it's atmospheres once again, so we're lucky they remain the same. Otherwise, we'd have to convert to make them the same. During the ascent, the temperature of the gas falls from an initial temperature of 22 degrees Celsius, which remember we've got to get that into kelvins. So 22 plus 273 is going to give us 295. And then it's going to go till it's negative 21 degrees Celsius. It gets cold way up there. So negative 21 plus 273 is going to give us 252 Kelvin when we get there. And then it says, what is the final volume? Calculate the final volume of the balloon at its final altitude. So this is our question mark. So notice it's a balloon that's sealed shut, and so the number of moles remains constant. We have initial and final conditions, so I know I'm in the combined gas law type problem. Now for these types of problems, I always like to solve for the final variable right here, and we're looking for volume 2 right here, the final volume. And so to rearrange this equation, I'm going to multiply this side of the equation by T2 over P2. And what I do to one side of the equation, I have to do to the other. So this is T2 over P2 as well. And then these cancel with one another, and we're left with volume equaling our temperature 2 times pressure 1 times volume 1 divided by pressure 2 times temperature 2. And now we can put our numbers in. So temperature 2 is 252 kelvins. Pressure 1 is our initial pressure of 1 atmosphere. And our volume 1 is 6 liters. And then on the bottom, pressure 2 is 0.45 atmospheres. Notice how my atmospheres are going to cancel with my atmospheres. And my temperature 2 is 252 Kelvin. Sorry, this is, I wrote this wrong. I've got T1 down here. My bad right here. This is T1. I copied that wrong from right up here. T1 right here. T2 is on the top right here. So my mistake, that should be T1 or 295 Kelvin down here. Thank you for catching that. So 252 times 6 divided by 0.45 times 295. We'll let the book do the work for us. And then after we rearrange that and put that in, we should end up with 11 liters. And so afterwards, our balloon increased in size from 6 liters to 11 liters. We never changed the number of moles of gas. Number of moles were constant in that, and that let me know that it was a combined gas law problem, not a PV equals nRT problem. Let's do one second problem right here. And this is problem practice exercise number 2. Practice exercise number 2. But first, before we start it, here's a common question I get from chemistry students. I'm not sure whether it's a PV equals nRT, perv-nert problem, or whether it's a P1 V1 over T1 type problem. Well, step number 1 is to just organize the data they give you. Organize it first. And so let's walk into this problem, and I won't tell you what kind of problem it is. Let's organize the data first, and then let's see if we can figure out if it's going to be one of these that's going to involve a solving for moles, or if it's going to be one of these where moles are constant and we just have changing conditions. So let's read through practice exercise number 2 and see if we can organize the data. 0.5 mole sample. Ooh, moles. Maybe it's this one. Let's just write that down right here, 0.5 moles. We'll keep that on the side. Of oxygen gas is confined at 0 degrees Celsius and 1 atmosphere in a cylinder with a movable piston. Now I want to pause right there because there are people that take this class that don't know what a movable piston is. And so I pulled up some pictures here of a movable piston. It's a cylindrical container, and then this object right here is called the piston, and that can move up and down. Here's another example of it. We have a volume right here with a piston pushing down on it, and it can move up and down, and you can see how that changes the volume of the container. The thing about the piston is it doesn't allow anything to go around the edges, and so whatever's confined inside of this container right here is stuck inside of there. So pistons are used in engines, and they actually like squish a gas and then they cause an explosion, and that's what causes your engine to have a certain amount of energy. So that's our combined cylinder with a movable piston. The piston compresses the gas so that the final volume, hint, they're telling me a final volume, they told me it's a cylinder that has a final volume that's half of its initial volume, and the final pressure is 2.2 atmospheres. What is the final temperature of the gas in degrees Celsius? All right, so originally we're going to start with some initial conditions here because it used the word final conditions in there as well, and we're going to try to fill in the pressure, the temperature, the volume, and we'll see if moles changes, but it sounds like it's a piston that doesn't allow any gas to escape, so it's going to start and end with the same amount of moles, which might mean that it's probably going to be one of these kind of equations because the pressure, temperature, and volume were given a whole bunch of data. But we'll see. Let's start to fill it in. It says it's confined at 0 degrees Celsius, so my initial temperature is 0 degrees Celsius, which is 273 Kelvin, and it's at 1 atmosphere, so my pressure initially is at 1 atmosphere. It has a movable piston. The piston compresses the gas, so the final volume is half of the original volume. Now, they don't give me actual numbers for the volume, but since it's half, the relationship between the two is going to be the same. So let's make up some easy numbers that are going to be, useful in here. And so the initial, let's just say it was 1 liter, and let's say that the final is a half a liter. So that's half as much. You could have picked 150 if you wanted to, just as long as the final is half the initial volume. And the final pressure is 2.2 atmospheres, so we're given a 2.2 atmospheres right here. Notice they used the word final in there a couple of times, which help you know that it's going to be this type of problem right here with some initial and final conditions. What is the final temperature of the gas in degrees Celsius? So this is our question mark right here that we don't know. Notice the 0.5 mole sample of gas was important, but we found out that it's a piston system and none of the gas escapes or no new gas comes in, and so the number of moles of gas doesn't change at all, so it can't be one of these types of equations or one of these kind of problems. All right, so P1 V1 over T1 is equal to P2 V2 over T2. we want to find the final temperature. So we want T2 right here. I'll multiply this side by T2, and that'll cancel these guys. And then I'm going to multiply this side of the equation by T1 over P1 over V1, and I'll do the same to this side. And if you notice, this, if I multiply T1 over P1 over V1, would all cancel out with each other. And so now my final equation ends up being T2 is equal to P2 times V2 times T1 from right here over P1 times V1. All right. Looks like I did my algebra okay, and now I can plunk in my numbers and make sure that the units match. The pressure 2 is 2.2 atmospheres. The volume 2 is 0.5. Remember, I made that up because I wanted it to be half as much as the original. Temperature 1, 273, divided by pressure 1, which is 1 atmosphere, and volume 1, which was 1, or it just needed to be twice as much as this one. All right, let's try that on our calculator. Let's see where we end up. So I think it's valuable sometimes to see you do this on the calculator here. 2.2 times 0.5, enter, times 273, enter, and then I'm going to divide by 1 times 1. Kind of nice that I chose 1 liter right here, but if you chose something else, then you'd have to divide. 300.3. So my final temperature in Kelvin, because notice my relationship here had to be in Kelvin, is 300.3 Kelvin. It asked for the temperature in Celsius, so subtract out 273, and I end up with 27.3 degrees Celsius. So we'll notice that it started at 0 Celsius and it got up to 23 degrees Celsius. It got hotter when those two items changed. Good luck with your combined gas laws.